We have major structural design changes, TMS 402-602-22. This is our program description and our learning objectives for today. Continuing education credits, we have one PDH and one AIALU HSW for you. Our provider statement as required. Certificates for everyone will be sent from myself, as well as I will report if you're an architect, I'll report your credit to AIA Online. And today we will also have business card giveaway for the 22 codes. So be putting your name or business card in a little plastic box that comes around. And our awesome sponsor today is Trends in Tile. Distributors of Latticrete International Tile, stone installation products, and real stone systems. Premier mortar beds and grouts, waterproof membranes, epoxy adhesives, and grouting systems. Natural stones from Stone Solutions, and thin brick from Metro Brick. Thank you. Joel Tully is not feeling well today, but he does have a table set out with brochures and some samples if you want to check it out on your way out. And for our special guest today, our speakers, Dr. Richard Bennett. Dr. Bennett has been on the faculty at the University of Tennessee, Knoxville since 1983. He is the present director of the Engineering Fundamentals Program and professor of Civil and Environmental Engineering. Dr. Bennett received his PhD and MS in Civil Engineering at University of Illinois, his Bachelor of Civil Engineering from Cleveland State University. Dr. Bennett is a licensed professional engineer in Tennessee and specializes in structures. He has done research in engineering education, masonry testing, analysis and design, structural safety, and reliability. Dr. Bennett has been very active in the TMS 402-602 Code Committee. He was also instrumental in going to a 6-year code cycle. He was the editor of the 2022 Masonry Designer's Guide and co-authored the new Street Design of Masonry. Dr. Bennett has received nearly every TMS award for his work and contribution, and it is quite an honor for him to visit and present to us. So please give a warm welcome to Dr. Richard Bennett.
So thank you for the very kind introduction, and it's good to be back. I think this is my 4th time here, if I'm right. So always enjoy being here and talking about the 2022 code. Today, sort of the structural changes. So here's the graph that I keep of code pages, and I was chair of the 2016 committee. So this is my 2 biggest achievements in my career. You know, 2016 had fewer pages than the previous edition. I don't know that there's any other structural code that's met that. And as Margie wanted, a group of us, Daryl was involved, went to a 6-year cycle. I mean, I have so much respect for you all. And how do you keep up with everything that's going on? You know, all the code changes and everything. So. And we are staying on the 6-year cycle, so the next code will be 2028. I know you really haven't adopted the 2022, but there are some things that we can actually apply now, so we'll look at that and so what's coming. So we did, unfortunately, increase pages a little bit, but at least the slope's pretty small there, not too bad with that. 3 things to know, and actually you've sort of will cover 2 of them. So I'll talk about tension and compression controlled sections and strength design. We're just chatting here. I forget how many years ago, but I did a talk, compared strength and design and allowable stress. I'll admit it, I'm a strength design sort of fan for a variety of reasons. The veneer chapter is completely rewritten, so I'm going to talk very little about that. Next week, Tina Subasic is here to talk about the veneer chapter. So there's some sort of things that will interest architects, I think, changes in the veneer chapter, and things that will interest engineers. And I'll just touch on it just briefly, but Tina will cover that in much better than I could next week. And then we also had an appendix on GFRP, glass fiber reinforced polymer reinforcement. I know, was it October sometime, John Myers talked on that, so I won't really do much on that there. But those are some of the big changes here. Here's sort of changes by chapter, so I'm going to focus sort of on the major changes that we have and highlight a few of those. We'll look at some related to reinforcement. We'll look at some seismic design things, and big one in strength design here. And then veneer was completely rewritten. Empirical masonry was deleted, appendix A there. We moved the masonry infill out of an appendix in there, and then we did add the appendix on glass fiber reinforced polymer reinforcement. So that's a big picture overview of some of the major changes in 2022. So I'll just pick some out as we go along. And I'm actually sort of happy to start with this one in Chapter 4. Chapter 4 is sort of general requirements, and we added in this table here, table/figure on shear area. And I really want you to hear the background on this, that Masonry Society gets questions from engineers sent to them, and then they parse the questions out to various people. I get a lot of the ones related to codes. And there's a couple questions where practicing engineers were just confused over shear area. It really wasn't defined very well, what they use for beams and stuff. So I said, well, if there's confusion, we need to sort of figure this out. And picture's worth 1,000 words, so I sort of developed this and actually worked with a couple of the structural engineers that sent in questions on it and got some review and some feedback and modified a few things. And this is what we ended up here. That hopefully clarifies some things there. So I'll talk a little bit about the table, but the big point that I want to make, I guess, to you also is I'm a sick person, I'm a strange person, I enjoy code, so give me your questions. If you're confused on things, ask questions. We will work to try to answer them. Maybe the next edition before it's in there and stuff does take time, but do let us know your questions, things that are confusing. At least some of us on the code committee really want to work and do that. So this is the result really of questions and a review by several practicing engineers and that. So hopefully it's helpful. A couple things just to point out: the net shear area. There's confusion on this, so that you have a partially grouted wall, and the in-plane area is the net mortar area. So we usually have just face shell bedding, and the area of the grouted cells. So sort of the area that's in the darker gray up there. So the face shell and then the grouted cells that you have there. You can't actually calculate it, or you can work off of sort of an equivalent thickness based on how much grouting you have to get the shear area there. So we tried to clarify that. And then the big one was the shear area for beams. So although we use the length of the shear wall for getting the shear area, the entire length for beams, as with concrete, we go to D, the depth of the reinforcement. We had some discussion about partially grouted beams, and we do allow that now. So the top and bottom course, this is probably in a sense not the best picture. If you're grouting the top and bottom course, you probably just fully grout it. But if you had a deeper beam, maybe you just grout bond beam right over the opening, a couple courses up another bond beam, and the shear area we're taking conservatively is just the face shell sort of area there. So we have a table there. Move to Chapter 6, which is reinforcement. Deformed bar size consistent, the size of reinforcement and grout, and then hooks. We'll really focus on the first two, and there were a few other things that we had there, but we'll focus on sort of the bold that we have there. So remember masonry, we have allowable stress design and strength design, and there were differences in sort of just prescriptive reinforcement provisions when you had ASD and SD. Like we had the 6% for ASD, and 4% for strength, but you're measuring different areas, and just sort of goofy. I don't know how else to say it, just sort of goofy. So we did harmonize those into 4 requirements. It used to be a maximum size. It was number 9 in strength, number 11 in ASD. So it's number 11. Now, that's rare. That's really rare. I mean, usually we're at 4s, 5s, and 6s, but perhaps a column or something that you did. So that's that. We had actually harmonized in 2016, so maximum bar size is 1/8 the nominal dimension, the thickness of it. So an 8-inch wall, the maximum you can put in is number 8, which is still pretty heavy reinforcing. And then we had some other sort of goofy requirements. So now we have 2 that it has to be 1/3 the least dimension of the gross grout space, or the maximum is 1/3 that. 4% of the gross grout space is the maximum reinforcing. Now, what is the gross grout space? Sort of a strange name, huh? And people have made some funny jokes about it, but we'll let that go. So the gross grout space, you read the definition, and I somewhat facetiously say, this is amazing code language, because it does actually say what it needs to say, and you can't understand it. So what is it? And so we have a picture for you in the commentary there. So the gross grout space is if you stand on top of the wall and look straight down, and just sort of the clear space you can see as you look down in a cell. So it accounts for sort of the offset of running bond, offset of the units and that, but it's what you see when you look just straight down, the clear space that you see there. We're not considering protrusions, we're not considering horizontal bars, just if you look, what's the area that you have there. So it does depend a little bit on the unit type, but whether you have running bond or not. Personal opinion, we may have dialed a little tight, but it is what it is. Now, the next thing is that sort of tells you sort of what it is, and then we have these tables here in the commentary. Just the fun of code writing. 7 numbers there, 7 levels of numbering to get the table. But this works out for standing units. So out of all these tables, we'll just focus on one number here. Flanged units, so that's the flange unit you have up there. Actually, we don't use those in Knoxville. I'm not sure about here, but we'll just take flange units. That's the most conservative. 8-inch wall, here's the number to focus on. So we meet those gross grout space requirements with the number 7 bar, that's the maximum. Again, that's probably more than we usually use, or 2 number 5s. So I can put that in my cell, and I've met those gross grout space requirements. If you need bigger, which is rare, you could then specify jam units and just have that as part of your specifications. But really the number I would focus on is sort of this number right here. I'm just saying 8-inch. You can look for other thicknesses and stuff, but that is really sort of the limit. So I think we've harmonized it, and hopefully sort of, even though it's the wording sort of goofy, hopefully this table, okay, just go that's what you can do. And really the idea is just to be able to, not have it so tight that you can't get the grout in there. Hooks for shear reinforcement. So we had in chapter 6 that if you had horizontal shear reinforcement, which is not real common, usually the masonry can carry all the shear, but sometimes you need horizontal shear reinforcement. And if you had to either have a 180-degree hook if it's at the end of a wall, if there's an intersection there, you had to do a 90-degree hook there. So this is goofy. You had to do that if you're designing by Chapter 9, strength design, but you do not have to do that if you're designing by Chapter 8, allowable stress design. And the technical reason is politics. That when it was moved from Chapter 9 into Chapter 6, the ASD people said, we don't want it. Yeah. Turns out ASD was right. So actually in 2022, There's nothing there. Blue sky. We got rid of the hook requirement. Okay, they're going to rear their ugly head when we get the special reinforced shear walls a little bit, but right now it's gone. It's out of Chapter 6, none of that. And the reason was actually research has shown that whether it's a hook, an 180-degree hook, a 90-degree hook with the extension going in the cell, a studded end, nothing special. Basically, it had the same shear strength there. So hooks are gone for shear reinforcement, but we'll get back to it with the special reinforced shear walls. And we did actually sort of clarify development lengths for hooks. Not a real major change that we had there. So that's Chapter 6. Chapter 7 is seismic design requirements. So the three that I'll focus on is shear capacity design, hooks and special reinforced shear walls. I told you he'd raise the ugly head again. And then non-participating elements. So I know you sort of in seismic design category C or D, sort of depends on where you are. But in D, of course, special reinforced shear walls are required in seismic design category D. And one of the requirements for special reinforced shear walls is the shear capacity design. So special reinforced shear wall, we're designing for R equals 5. We get to reduce our forces by, divide by 5. Why do we get to do that? Well, it's ductility. We have energy absorption. And the way we absorb energy is essentially a plastic hinging, a flexural yielding of the wall there. Well, we don't want a brittle shear failure first before we get sort of the hinging and the yielding of that. So that's the whole idea behind shear capacity design, is essentially we're doing that. So there's a couple changes that I'll mention. First, every place else in the code, we would deal with allowable stress design first and then strength design. The order was reversed here. So we just reversed the order. For allowable stress, it was 2, now it's 1, no big deal there. We increased the forces by a factor of 1.5 with allowable stress. We've changed that to 2. You should be up in arms over that, right? We've increased that, but we got your back here. So in 2016, we cut the allowable masonry shear stress in half for special reinforced shear walls. It was a half for all the other walls, and then a half of that, a fourth that, and that's gone. There's, again, sort of politics. The 1.5 was a historical number that had been around since, I don't know, came down with the 10 Commandments to Moses on the stone tablets or something. And when we recalibrated in 2011, sort of our allowable stresses, there would be a big pushback if we didn't keep the historical 1.5. So to match strength design, we went with this with a quarter. It really didn't do a very good job of that. So finally we just said, forget it. Got rid of the 1/4, but we're doubling the forces. Actually, the net is for most walls, there'll be a little bit less shear you're designing for out of that. And then for strength design, again, we moved now strength from 1 to 2. But we had the design strength. Design is the strength reduction factor times the nominal strength. It's less than a value, the shear corresponding to 1.25 times the nominal moment. And then we had the nominal shear strength, which is without the strength reduction factor. And that was confusing. Why do you do design strength once and the nominal strength here? So we changed that. So it's design in both cases, but 0.8 times 2.5 is 2, so the provision has not changed, but hopefully it's a little bit clearer that we're using design shear strength in both places. Now our hooks. So in 2016, shear reinforcement shall be anchored around vertical reinforcing bars with a standard hook. And I don't know how many of the hours of my life I've lost in hearing arguments on two things with this provision. Is shear reinforcement, does that mean all horizontal reinforcement, prescriptive reinforcement that you have to have in a special reinforced shear wall? Or does it mean just the reinforcement required to resist shear? So if the masonry has sufficient shear strength, you don't have to worry about this. And there's very, very strong arguments on both sides of that. And then standard hook. Does a standard hook have to be a 180-degree hook? Can it be a 90-degree hook with the leg going sort of down into the cell? And there's very, very strong arguments on both sides of that, too. So we did actually end up changing it. So we got rid of this, and we're clarifying when hooks are to be required. So essentially when V over A sub n, V sub n, F sub Vm for ASD or V sub U over that. So essentially what we're saying, whether you're doing allowable stress or strength design, is that when you're 40% or less, then the demand is 40% or less than the capacity, don't have to put in hooks. When it's 40% or greater than 40%, you do have to use hooks. Now, that seems maybe like that's pretty stringent, but remember we just talked about the shear capacity design, so I'm doubling the shear anyhow. So let's just put some simple numbers of it. I'll make it. So suppose my shear strength from the masonry is 10 kips. We'll just make up a number, okay? So remember I have to double my shear demand, my shear force. So when I get up to a shear force of 5 kips, 2 times 5 is 10, then I'm at the limit of my masonry shear strength. So if I'm at 5.1 kips, double that's 10.2, then I have to put in some shear reinforcing. Okay, so at half, essentially, of strength, I have to do that. So this is saying now at 4 kips I do, so it's a little bit less than that when I really need shear reinforcement, but it's pretty close to it. So if I get close to needing shear reinforcement, then I have to put in hooks on that. And the hooks were the 180-degree and what we had in chapter 6 there. So for special walls, when our shear is greater than 40% of the shear strength of the masonry, we have to do hooks. I'm an old man, so I get to tell stories, right? This happened in the last code committee meeting of the cycle. And the provision, over objections from myself and 2 other people, this actually, all they had was really the last sentence here. The termination of horizontal reinforcement embedded in grout shall meet one of the following to meet the hooks. That means all reinforcing, prescriptive reinforcing had to have hooks, okay? And basically the argument of 3 of us was, big box structure, it's stressed to 15% of the shear capacity or something. Why are we worrying about hooks? We have so much extra capacity here. But that's what got an over objection. So then we had this last code committee, and it's weird, our procedures. We had several ballots, like keeping that, or 20%, the number here, 40%, or that. And so actually one of the 3 wasn't at the meeting, so it was down to 2 of us. And so we went in that last meeting. We were hoping maybe we could convince them to get the 20%, if it's below 20%. And as the discussion went on and people started to realize what the actual provision was requiring, saying, you mean I have to put a hook on every horizontal bar? Yep, that's what it says. Wait. Of course, I'm also thinking, you voted for this. You know, on the code committee, did you read it? But that's all right. We'll give them slack. Anyhow, got enough going on. We ended up with 40%. I was ecstatic. and that. Few people in California were really mad, you know, so I was considering it a win-win, you know. Got hooks out of a lot of walls, and I got some people from California mad. So it was a good day for that. Anyhow, so that's what we have there. We did clarify for non-participating elements. It said that non-participating masonry elements like a shear wall, not shear wall, partition wall or something, that the prescriptive reinforcement had to be either horizontal or vertical. Really the intent was to be in the direction of the loading. So most partition walls span vertically, not all, but most span vertically there, and putting in horizontal reinforcement really doesn't do anything for you if it's spanning vertically. So we've clarified that it has to be in the direction of the span. Now it is pretty sort of light reinforcing there. Number 4 is at 10 feet, so it's not huge reinforcing that you need there. If you have to put in I shouldn't say if, in seismic design category C, you have to do it. But actually take advantage of that. So there's 2 ways you can really design partition walls. I mean, you could design it as unreinforced, and then you just throw a bar in at every 10 feet. But if you're going to have to put the bar in at every 10 feet, actually take advantage of it. That'll help you and get you more strength than using unreinforced. All right, chapter 8, allowable stress design. We have here, we had a few changes there. We changed the maximum, this was 0.25, and sort of calibrating with strength, we increased that to 0.3. You're rarely up there anyhow, so it really doesn't matter. We did talk about that masonry shear strength. That was 0.25, and it was changed to 0.2. That's really a load combination issue. You know, in allowable stress design, you have 0.6 wind or 0.7 earthquake. So you can't really make it work as such. ASC 7 actually last cycle had 2 ballots to change the ASD load combinations to the strength combinations divided by 1.5. Both ballots failed. It's still being discussed. I don't know what's going to happen in 728, but probably somehow the ASD will change. But anyhow, that's sort of a load combination issue there. In chapter 8, we said about the shear for a beam. You could look at D over 2 from the face of the support. So technically that didn't apply to strength design, but we moved that to chapter 5 and that. And then some things that happened in both chapter 8 and 9, allowable stress and strength design. One is anchor bolts. 2 truths and a lie if you've played that game. Actually, I have 1 truth and a lie here. So the commentary to chapter 9, or maybe I should back up, our anchor bolt strength was based on Fy. You know, in AISC and ACI, it's basically the strength of steel is based on Fu. And there's not a real good well-defined yield strength for like A307. So our commentary said use a yield strength of 37 and it will match basically that in AISC. A couple of sections down, it said use the effective tensile area. Not the gross area of the bolt, the unthreaded portion, but use the threaded portion. One of those is a lie. If you use the threaded portion, 37 KSI, you get about 75% of the strength of AISC. So one of those is a lie. You choose which that. But we did change the F sub U based on that. So now anchor bolts, the steel tension or shear, the steel has the same strength whether you use AISC, whether you use ACI 318, or whether you use TMS 402. That makes sense there. So we did change that. And we do use the effective cross-sectional area, so we do have a little table there for common bolt sizes, anchor bolt sizes that would be used in masonry. Reinforced masonry shear strength. So in 2011, I believe it was, we introduced gamma sub G, this partially grouted shear wall factor. So it turns out, when we were looking at it back in 2011, we looked at about 8 different ways of calculating the shear strength of a masonry wall. And probably by pure luck, strength design did the best. Beat out Canada, beat out Australia, beat out New Zealand, beat out Priestley's equation. It was good. So we actually then changed in 2011. So ASD now is basically mirrors, for in-plane shear strength, mirrors strength design. We divide by the area to put it in terms of stress and use a factor of safety of 2. It worked really well for fully grouted walls. So it turned out that the strength design equations for fully grouted walls was about 14% conservative, roughly. That's some work that Dave McLean at Washington State, one of his students, did. In other words, if I build a fully grouted shear wall, took it to the lab, tested it, determined the strength on average would be about 14% greater than what we predicted. Now, there's a lot of scatter on that, so that. Now, partially grouted was not so, and we were going, skies falling, and so forth. So there's some work done at Drexel, and these showed for partially grouted shear walls that we only predicting, essentially under-predicting. We only predict the capacity was only about 90% of what we predicted. In other words, again, if we tested a partially grouted shear wall in the lab, that it would only test on average about 90% of what we were predicting. All right, so we had discussed this and what are we going to do, and I got frustrated at one code committee meeting, remember San Antonio, and basically if you take 0.9 divided by 1.14, sort of the ratio there, you get like, I think it's 0.77, so well, we'll round that to 0.75, just reduce our partially grouted for shear strength for partially grouted walls to 0.75. And we adopted it, and that's what it is. So that was literally the amount of work that went into 0.75 that we had, okay? So there's a PhD thesis written, Patrick Dillon, whoops, I got ahead there, hit the button, re-examining this. And actually, I reviewed his PhD. I'll give Patrick credit. He did a lot of work. He probably did actually the work of 2 PhDs. He really did a lot of work in that. But the conclusion of his PhD was our factor should be 0.7 instead of 0.75. He looked at a bigger data set, a little more rigorous statistical analysis and stuff that we had there. So we changed to 0.7. Not to sound like an egotistical jerk, but I was sort of pretty proud of myself that in 2 minutes I could come up with pretty close to a PhD or something. But, I've ribbed Patrick about it too and stuff. My pet peeve, why in the world does every code change either increase the load or decrease the strength? It just seems like everyone does that. So boo, get rid of it or something. But we have one that actually we increase. So for shear friction strength, that 0.6 there increased to 0.75. So the crowd is going wild here. We actually have something that increases the strength a little bit that we calculate that. And we actually changed for strength design the shear friction strength. We had this, which was not too bad to calculate, but a hard thing to calculate this area, so we made it a little bit easier. I'll cover tension, compression, controlled sections a little bit later. Just a few things on Chapter 9 and a few other chapters. We did change, if you do an out-of-plane slender wall in strength design, you have to crack moment of inertia. That T sub SP over 2D was a modification for non-centered reinforcement, empirical. One of our members derived this equation, sort of mechanics based for non-centered reinforcing. So even though the equations look different for centered reinforcement, they actually reduce to the same equation. So we really didn't make a change there. Masonry veneers, I said you'll get a great talk on that next week. We completely rewrote the chapter. Just to whet your appetite, I think we made it a little simpler in how you do design. You can use the 2022 provisions, even though you're still on 216 in 2016. If you go to this, essentially the alternative design of anchored masonry veneers. So that actually is a path that you can use 2022 now in that. So there's some things related to stability of backing. We have a table. Said you had to consider that, but didn't tell you how, so we got a simple table. We also came up with an engineered design method for veneer ties that can save you quite a bit over a prescriptive design, reduce your ties there. Again, I'm not going to spend time. Here's Memphis, Tennessee, an example that using the engineered approach, I was actually able to cut the number of veneer ties in half. There's also a modeling approach that we have and describe that. So I go through that. I know I went through it real fast, but hopefully it whets the appetite a little bit, and come back next week and hear Tina talk, and she'll talk about this. There's also some architectural sort of features that we added in there that I think will help a lot. And we did add the GFRP, and of course John Myers was here. A few things in 602, the spec that changed. We did add periodic inspection for anchored and adhered veneer when the height of the veneer is 60 feet or more above the grade plane there. We did, of course, add things on GFRP. We added in pre-blended mortars, C1714. It really was in there, 1714, references 270, but just to be clear. So the pre-blended, you know, you get the sack. A lot of, at least around Knoxville, a lot of people are using it with a silo. You put it in there, that. So we also added in F1554 for anchor bolts, that, some other things in there. We clarified some things on stainless steel joint reinforcement. Stainless steel is really interesting that the yield strength's half or less of the ultimate strength for a lot of stainless steels. So it's sort of an interesting animal to deal with. We did some things on wire reinforcement, just clarified some terminology, and a few other clarifications, tolerance for veneer tie placement, and that. And I'm going to submit this. If there's ever a contest for the worst PowerPoint slide ever, I'm submitting this because I know you can't read a thing there. But I want you to understand that this is actually, I think, a very helpful table. So there's just really confusing. We talk about grout pour heights, grout lift heights, and what can you do? Pour is the amount you do in one operation, but you do it in lifts. But we call it low lift and high lift grouting, which doesn't make any sense. It's just real confusing. So John Chrysler, I know he's spoken here before, came up with this picture here, this table that really clarifies all of the grouting, sort of the high lift, low lift, what grouting procedures can you use. So it's really helpful. I know you can't read it there. And we will be referenced in, or I referenced, I shouldn't say, it's out. We are referenced in that. All right, we'll spend the last little bit here on tension and compression controlled sections. So I am a fan of strength design for a variety of reasons. It gives more efficient, potential to give more efficient designs than allowable stress. As an educator teaching a masonry class, it's pretty similar to reinforced concrete design. So it's a little easier to teach. In 2016, we had some pretty stringent maximum reinforcement requirements in strength design. Our strength reduction factor for combined bending and axial load, flexion axial load was 0.9, period. You know, think of ACI 318. It's 0.9 for tension controlled, but then you have your transition region and your compression controlled sections, lower strength reduction factor. We didn't have that in masonry, but we had some stringent maximum reinforcing requirements. That we had that the strain gradient corresponding to epsilon u and alpha of 1.5 times the yield strength there. You know, balanced conditions would be the steel strain is yield, and so we're less than balanced here. We had this weird load combination. You could include compression reinforcement in calculating maximum reinforcement. Really, those all came about to make it work. When we introduced strength design in 2002, you really couldn't design. The maximum reinforcement provisions were so stringent that if you put in much more in the number 3 bar, you exceeded it. And so it wasn't workable. So this came about, so basically it can work. Now, sometimes those are really restrictive. So let's see, it's about 5 years ago, there was a group of 14 of us that got together, and we spent a week together up in a rental house in Canada. And there were 7 from Canada, 7 from the US, and we compared the Canadian and US masonry code. Bunch of sick people, right? Just spending a week living together, comparing codes. Great time. We kicked Canada's rear end. It was not close that you know, our designs were so much more efficient than Canadian designs. And Jason Thompson, probably most of you know who he is, talked to some. We sort of had an epiphany that we had made sort of a bunch of minor changes over the years, sort of enhancing it, and they added up so we could kick Canada's rear end. Except we did a four-story, or we did a structure, apartment building, and sort of how high you could go. And Canada could go higher than we are. And it was these maximum reinforcing provisions that were biting us. So that we were starting to do it, but there's a motivation. We got to do something about here. So we introduced this tension and compression control. Here's the interaction diagram. Number 5, 8-inch CMU wall. Number 5 is at 8 inch. Looking at out of plane loading here. So number 5 is at 8 inches. Reasonably heavy reinforcement, but certainly something you can have at jams, at piers, and it's not unheard of either. And the interaction diagram with the maximum reinforcing provisions was this dotted line here. It was all in the tension region. So that means to make number 5s at 8 inches work, you had to have permanent tension. Only case I know of that is universities. All the hot air from professors sort of creates this permanent uplift on that. I mean, you couldn't do it. And there's no way out. You had to go to ASD. You're no way out. So you couldn't build this. So that was sort of the motivation. So this solid line is now with the tension and compression controlled sections. And you can see we gave up a smidge here, but boy, we gained a ton. Okay? So that was, there's several other motivations, but this was one of the big ones that we have here. So here's the provisions to be just like pretty much ACI 318, that we have a table of the strength reduction factors. You can take the strain, the yield strain for grade 60 is 0.002 if you want. And then we have this funny 91442 about less than 0.65 P balanced, and I'll explain this goofy section in a little bit. It really needs to be in there, but it really doesn't do much either. I'll explain that in a little bit there. But here we have tension, transition, compression control, just like we have with concrete. And if you're doing an interaction diagram, you can also write it in terms of C, the depth of neutral axis, over D sub T. I use this a lot sort of in spreadsheets to do the interaction diagram. As a result of that, we deleted the maximum reinforcing requirements for out-of-plane loading, for ordinary reinforced shear walls, for columns and pilasters. We did maintain the maximum reinforcement ductility requirements for intermediate and special walls. I'm going to look at those a little bit and give you a little trick there. And we did say that beams, like ACI, does need to be tension controlled. So we'll look at that briefly with beams and lintels. Beams there, actually it's a little more stringent. There has to be tension control, but these values are easy to meet. So from a practical standpoint, really no change there. If we look at load-bearing walls, so there's some formulas in the commentary, but this is the maximum load on a load-bearing wall for it to be tension controlled. So if you exceed this load, then you're in the transition or compression controlled region. Now the color coding is mine, so you can argue with that. But green basically says that you're going to be tension controlled. I mean, look at these loads, 10 kips per foot, 14 kips per foot. Think of a single story, big box structure. Your axial load is what? On the order of kip per foot-ish in that. So we're nowhere near this. So we haven't changed most of the design you do out of plane. It's going to be tension controlled, okay? So almost all walls you do it still the same way, tension controlled. The yellow there, the 1.2, 1.4 kips per foot, well, that's sort of close to where your loads are. So you might get in the transition region, you might not. And then the red, you need pure tension, so you will be in the transition or compression controlled region there. But you can design for that. So 16-foot, 8-inch high wall, 700 pound per foot dead load, 300 pound per foot live load, roof live load, out of plane wind load of 30 PSF, sort of some generic, roughly typical numbers. You end up with number 4s at 48, And just by looking at that, there's no way any load combination is going to be greater than 14.5 kips per foot axial load. So it's tension control. Easy. We're going to come back to that a little bit. Now, we'll skip over this. Now, that funny section I mentioned. So if you draw an interaction diagram for the number 4 is at 48 inches here, do that you end up with this goofy little, this dashed line here, okay? What is happening, and this only happens for partially grouted walls. John Huckwall, I think he may have, I believe he's spoken here too, proved that couldn't happen with fully grouted walls. But here's what happens. As the neutral axis increases, as the neutral axis gets bigger, with the partially grouted wall, then the neutral axis ends up in that grouted cell. And there's only 1 out of 6 cells that's grouted. So think of like a T-beam, a pretty narrow web in there, okay? So as that neutral axis increases, you're gaining a little bit of axial load, but not much, because that web's real smaller. You're just not gaining a whole lot of area in there. So the axial load is going up pretty slowly. But we're in that transition region, so C increases, that strength reduction factor is decreasing. You know, we're going between the 0.9 down to the 0.65. So essentially what is happening is that the axial load is increasing at a slower rate than phi is decreasing. So you get this funny shape where it goes up and goes back down. Well, this doesn't make any sense. You know, so if you come across here at an axial load, you're good, then there's a region you're not, then you're good, then you're not again. So I'll just do wind loads. So this would be like saying, well, as long as you're below 100 miles an hour, your wall is good. Between 100 and 103 miles an hour, it's no good. But between 103 and 107, it's good again. And then greater than 100, you know, just silly. So all that section is saying is you can't do this little thing here. You just have to go straight across right there. So it's probably necessary. You got to guard against it. But it really never comes into play in a sense, too. If you're drawing an interaction diagram and looking at it, you're going to say, well, the computer generates that. Well, forget that little nose up there anyhow. That's what it's doing. So go back to that wall that I had, that 16-foot high wall, 16 foot 8 inches. Now we'll put some openings in it, okay? And we have a pier here, a 2-foot pier. So looking at out of plane load and the tributary on that. So number 5 is at 8 inches is what I need. So prior to 2022 and 2016, strength design, I'm toast. I can't do anything. I got to go to ASD. ASD ends up being more conservative than strength design. So this makes 0 sense. I say I can't put in the reinforcing because it exceeds my maximum reinforcing requirements. So I'll go to ASD and I'll put in even more reinforcing. Doesn't make any sense at all, but that's where you were at. You didn't have a choice there. And it works. There's my interaction diagram. My load combinations are in there. Number 5's at 8 inches work. How do you design with tension, with transition and compression control regions? It gets a little messy in that. And whatever you do in concrete works here in a sense. But the way I do it is with a spreadsheet and an interaction diagram. If I'll put my email address up, I'll send it to you. Happy to do that. But, you know, just sort of fooling around on a spreadsheet, sort of the bar spacing, in a few minutes, I'm there. You know, get it to work there. So in 2016, we were toast. Now we number 8, 5 inches in the transition region. So it works. Just a few minutes on shear walls here. So I mentioned in 16 we had these stringent maximum reinforcing requirements. Reasonably stringent. That was in 9332 and 936 wall designs for in-plane loads. You either had to meet this or there was this section on boundary elements, similar to reinforced concrete boundary elements. The only problem is in masonry, we don't have really enough research and knowledge to have prescriptive requirements for boundary elements. So pretty much, it doesn't say it explicitly like this, but pretty much what it says is if you're going to use boundary elements, you got to test it. Nobody's going to pay to test it in the lab to show you ductility. But there are some sort of checks, as it were, that if you meet certain requirements, actually then the wall is basically deemed to have sufficient ductility. So that was sort of hidden. It was in 2016. It is in 2016. It's sort of hidden, so we did some rearrangement here. So with shear walls, we have then a section on ductility requirements. And it only applies to intermediate and special, not ordinary. And you either have to comply with the maximum reinforcement requirements of 93561, which is the same as what we had, except the ordinary is gone, or the alternate, we're now calling it alternate approaches to ductility, which is really the same thing. But we just hopefully made it a little clearer. And I'll summarize all of the requirements in sort of this flow chart here. So you're designing a special reinforced shear wall, okay, and you got to check for ductility. So here's how we do it. Here's how I would suggest you do it. And this applies with 2016, but wasn't near as clear. And I think many people, I know a lot of people missed it and stuff. So there's a check that we have here, mu over vu L sub w length of the wall. Think of a cantilever wall, okay? The moment is the shear force times the height of the wall. So this ratio is basically a geometric ratio for cantilever shear wall, height over length. So as long as your height over length is less than 1 and your shear wall is longer than it is tall, you meet that. If not, then you can, if it's less than, if the length is greater than 1/3 of the height, then you can get in here. And your axial load is moderate, and I'll use that word. That's actually pretty generous, 1/10 of F prime M. That's 200 PSI over, if you got a fully grouted wall, 12 inches times 8, roughly 180 inches, times 200 PSI. That's a lot of load, okay? So most of it, we meet it. If you meet that, you have sufficient ductility. The code says you have, that's deemed to comply. You don't have to do boundary elements, you have sufficient ductility. So if you're doing a special wall, that's the first thing I would check, okay, is that. That takes you 2 minutes, 3 minutes to check. If it works, you're done. You have met your ductility requirements. If it doesn't, then this is actually similar to ACI 318, but it's in there. Essentially, you're doing P over A plus MC over I. If the compressive stress is less than 0.2 F prime M, then it says you have sufficient ductility. You're done. If you don't meet that, then you're in the maximum reinforcing provisions. Probably the easiest way to do it is based on your strain condition, you can then sort of calculate where your neutral axis would be for that strain, and then similar to sort of an interaction diagram, calculate the axial load corresponding to that strain distribution and see if your axial load from this goofy load combination meets that. And then you've met that. So again, this is not a technical change. It's a reformatting change. They hopefully make it a little clearer to you that there are these provisions that make it pretty easy for checking ductility of a shear wall. And if you have an ordinary wall, the loads are pretty high before it's not tension controlled. So again, I'll make up a number. 98% of your shear walls, the design won't change. I have no idea what number is correct or not. All right, whirlwind tour there. Thank you. What questions do you have?